not too, no, it's not too challenging.
Yeah. Doesn't seem too bad. Right.
Now for a bonus problem, all I did was I changed the problem a little bit. I moved the vertex number 4 from here to here. Now it becomes a bit more of a pain.
Darn.
You may not be able to see why, but once you try to do it, you'll know. So
yeah, that's just
it doesn't take much to take a reasonable problem into something that's kind of terrible. So, okay, and I also want to mention the next problem after that, problem 7, where I described it mostly verbally. You have a sphere of radius 3, and it says if you drill a hole through the middle of it, that's a radius 1. Okay, then here we have a cylinder described by the equation x squared plus y squared is equal to 1. And then here we have a sphere, x squared plus y squared plus z squared is equal to 9. So the idea is, if what's best to do is try to compute the volume of a region that's actually been cut out, and try to work with that. What you're actually asked to compute the volume of is everything else in the sphere except for what's been cut out. But if you try to do that directly, you might be in for a very difficult time.
that doesn't sound too bad.
Well, no, there's some that aren't so bad, and then there's some that are. Okay, and just a reminder, on the Thursday after break, I will do the review session thing. Who's here could not make it on Thursday? Anyone?
You said you were also going to do it on Wednesday, right?
What?
In the email, you said you were also going to do it on Wednesday.
If it's needed, like if there's people who can't make it.
What's the
Oh, like 6:30.
So should I like attend this review session and record it, or?
That would be nice, yes.
Okay.
I'm sure that some people in the class would like that.
They're probably YouTube only
Oh, okay, yeah.
because of time constraints for the test.
Okay, yeah. So after review session, you'll still have a week, plus late days. All right. So after today, we'll have covered everything. So you have enough material to do all the problems except for the last 2. So that's what we'll talk about now. Okay. So we've talked about a few coordinate changes. And in all of them, what you've had to do when you convert an integral to those other coordinates, it's necessary to multiply the integrand by the appropriate factor. So we did polar coordinates, so x, y goes to r theta. You have to multiply the integrand by r. We have cylindrical. So x, y, z goes to r theta z. Again, you got to multiply by r. And then spherical. So x, y, z goes to rho theta phi. You have to multiply by, get a little more involved, rho squared sine phi. So we've been using geometric arguments to establish what you multiply by, but generally speaking, that's going to be a real pain. But fortunately, there's a more systematic way to go about it. Is if you have any change of variable, how do you figure out what to multiply your integrand by? All right. So remember, from a single variable, you have a substitution. U is equal to g of x, then you get du is g prime of x dx. And if we assume that x goes between a and b, u runs between alpha and beta. So it's simplest in the single variable case because either way, we're just talking about intervals. So the integral from alpha to beta of f of u du is comes the integral from a to b. We write everything in terms of x now, f of g of x, and then this factor of g prime. That is what you have to include. So the single variable case, it ends up being the derivative of whatever function you have that describes the substitution. So you might think, well, if we're making substitution in several variables, we're writing, describing new variables u and v in terms of x and y, for instance, that you want to do something similar. So here, we'll take our function, we'll change from old variables to new, and then we've got to multiply by something, and that something should be related to the derivative of a transformation. Well, in several variables, though, the derivative is not just a function, the derivative is actually a matrix. It's the Jacobian matrix of all the first partial derivatives. We're not going to multiply this by a matrix, we're going to multiply by its determinant, in fact. So let's look at a two-variable case. Yes.
The change in spherical.
Yeah.
Is it,
Oh, yep. Oops.
okay.
Okay. There's a square in there somewhere.
You've been in this city too long. You're so relaxed. You just throw them anywhere. No.
It is 1 year ago today that I first set foot in Hattiesburg.
Really?
Yeah.
You any different?
What?
You any different? Do you like crawfish more?
No, and that's a problem. So.
Do you drink sweet tea or unsweet tea or?
No, I let Diana handle that. She's a tea drinker of a family. I do eat a lot more sausage, though. Okay. So let's suppose we have a rectangle in u and v. And we'll call this d tilde, and it runs from a to b in u and c to d in v. And we have a mapping to some region d in x and y. Okay. And the transformation is described by x is equal to function g of u v, and y is another function h of u and v. So what we have here is a generalization of what's going on here. We have an integral with respect to x and y, a double integral over d. But d is some complicated region. Maybe it's too complicated to handle using the method that we've talked about before. So we'd like to rewrite this as a double integral over this much simpler region, d tilde, which is a rectangle. And now x is going to be replaced by g of uv, and y is going to be replaced by h of uv. And then we need to put something in here and then integrate with respect to u and v. So that's what we want to get a handle on, is what is that something? So what we're going to do is look at a portion of this domain, a rectangle of dimensions delta u and delta v, which is mapped by g and h to some region. Generally it's going to be a curved region. It's not necessarily going to be a quadrilateral of any kind. So this whole thing should represent the area of a piece such as this. So when we're